Hello, and welcome to Business Calculus, the first derivative test. As we have seen, the local extrema, or turning points, of a graph are tied to the sign of the first derivative, f prime. If the derivative of a function changes sign about a critical point of the graph of f, then we know that that point represents either a local minimum or a local maximum of the graph. This makes finding local extrema very easy, as all we need to do is examine the sign of the first derivative, f prime, of the function. We call this procedure the first derivative test. Here we have some examples. We're going to have c representing a critical number of the graph of f, to where either the derivative at c is equal to 0, or the derivative at c does not exist, and then we construct the following sign charts for a function f prime. We have the following facts. If the function switches from decreasing to increasing, which means that the first derivative switches from being negative to being positive around the point c, then f of c is going to represent a local minimum. If it is the case that the function switches from increasing to decreasing, whereas we have f prime switching from being positive to being negative, we see that f of c is a local maximum. But in the bottom two examples, the function is either decreasing the entire time or increasing the entire time, which prevents f of c from being a local extreme. Here are some graphical examples to illustrate our point. In the first example, on the upper left, we have the function switching from decreasing to increasing, and we see that f of c is a local minimum. In the upper right, we have that the function switches from increasing to decreasing, and we see that the function is a local maximum. In the bottom two examples, the function is either increasing the entire time or decreasing the entire time, and we see that there is no small neighborhood around the point where that is either the largest value or the smallest value, so f of c is not a local extreme. Here we see some more examples. And you'll notice the open circles indicating the fact that the derivative at the point c is not defined, either because we have corners or vertical tangent lines. In the upper two examples, the function's continuous, but comes to a corner at the point, switching from decreasing to increasing on the left and increasing to decreasing on the right, and we see that the point represents a local minimum on the left and a local maximum on the right. In the bottom two examples, we have continuous functions that increase the entire interval on the left and decrease the entire interval on the right, and we see that there is no small neighborhood around the point in question where it is either the largest or smallest values, so f of c is not a local extreme. Let's look at an example and determine the following about the function f of x equals x cubed minus 6x squared plus 9x plus 1. We would like to find the critical numbers of f. We would like to find the local minima and local maxima of our function f, and then we would also like to sketch a graph. We start by taking the derivative of our function. The derivative of x cubed is 3x squared. The derivative of negative 6x squared is going to be negative 12x. And the derivative of 9x is 9, and we know that the derivative of 1 is equal to 0. Our goal is to find where f prime is equal to 0, or it is not defined. Since f prime is a polynomial function, we know that there are none of these points where the function is not defined, so we're just interested in where the derivative is equal to 0. So we are going to set the derivative equal to 0 and solve. We see that I can factor out a 3 from each of our terms. Which leaves us with 3 times the quantity x squared minus 4x plus 3, all equals 0. And if we continue factoring, we see that the function factors into x minus 1 and x minus 3. Negative 1 times negative 3 is positive 3, and negative 1 plus negative 3 is equal to negative 4. So this tells us that the derivative is equal to 0 when x equals 1 and 3. So we have found the critical numbers of our graph. We're going to be doing part B on the next page. And so here we have our critical numbers, x equals 1 and 3, and our derivative, which I have written in its factored form. Next up, we're going to want to determine the local minima and local maxima of our function f. To do that, we are going to be constructing a sign chart for f prime. And we are going to graph on our sign chart our critical numbers. So we have 1 and 3. Now what we'd like to do is plug in a point from each of those intervals to determine if our function is increasing or decreasing in those regions. First, we pick a number that is less than 1. We're going to choose 0. So we have 3 times 0 minus 1 times 0 minus 3. We have a positive times a negative times a negative. So this is going to be positive. So the function is increasing in that region. Next up, we choose a number in our second region from 1 to 3. We will choose 2 and plug that into our derivative. So we get 3 times 2 minus 1 times 2 minus 3. This is positive, this is positive, and this is negative, which tells us that the entire product is negative, so we get a value that's less than 0. So we know that the function is decreasing on that interval. And then lastly, we plug in a value in our final region from 3 to positive infinity, and we get 4 minus 1 times 4 minus 3, which is positive, 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 which tells us that the whole thing is positive, and we see that the function is going to be increasing on that interval. So to collect our first results, we know that the function is increasing from negative infinity to 1 and from 3 to positive infinity. The function is decreasing between 1 and 3. All right, now we would like to find our local mins and maxes. At x equals 1, we see that the function's switching from increasing to decreasing, which means that there must be a maximum there. And at 3, the function is switching from decreasing to increasing, so there must be a minimum there. In order to determine those values, we evaluate the regular function at 1 and at 3. So we're going to get 1 cubed minus 6 plus 9 plus 1. So we get 1 minus 6 plus 9 plus 1. And if we simplify, we get 5. Next up, we evaluate the function at 3. And we're going to get 3 cubed minus 6 times 3 squared plus 9 times 3 plus 1. So we're going to get 27 minus 54 plus 27 plus 1, which is equal to 1. So we have a local maximum at the point 1, 5, and a local minimum at the point 3, 1. All right, now what we're going to do is collect this information and use it to sketch the graph of our function. So the most important ordered pairs on our graph are the points 1, 5 and 3, 1, which represent the local minimum and local maximum of our function. We know that the function is decreasing on the interval from 1 to 3, so that we can sketch that part of the line. And we know that the function is increasing from negative infinity to 1, and we try to do our best to make it look like some polynomial function. And then down here, we know that the function is increasing on the interval from 3 to positive infinity, so we draw it increasing like that. Now, the important thing to recognize about this is it's just a sketch. It's supposed to be a rough drawing. The most important pieces of information are the fact that we know exactly where the turning points are, which vastly improves the quality of our sketch. Eventually, we will care about things like the intercepts of the regular graph to make sure that this point is in the right location. But for now, this is all we're looking for. We're just concerned with getting those 2 points in the correct location. What I would like for you to do now is to use what we've just learned to determine the local minima and local maxima of this function, f of x equals x cubed minus 9x squared plus 24x minus 8. Here are some potential responses. Thank you very much for listening. I'll see you next time.